Good morning. Happy Friday, everybody. Welcome to the TVE Happy Math Hour, our weekly interactive math reviews for Math 1332 and Math 2412, presented by Ms. Yvette Chuca, Mr. Ruben Carizales, and Mr. Albert Isasi. This session will be recorded so that you may come back to it later. Also, it is recorded so others who may have missed out today on today's session will be able to come back and watch it. Thank you. So now at this time, please mute your mics for best sound experience. Otherwise, the feedback could interfere with the information we will be sharing with you today. Without further ado, let's begin.
Hello, everyone. Happy Friday. Welcome. They will be posting a link for the 2412 course. So if you are here for 2412, then make sure you click the link to go to the other room. If not, this is going to cover 1332 set theory, basic properties of sets, complements, and subsets. So we'll get started here. And my name's Yvette Chuca, and we're going to cover some of these topics. Okay, let's see. So for most of the session today, when we're looking at sets, we have to understand a lot of the definitions. And so throughout the presentation, you're going to see that there's a lot of definitions, but the definitions are important in order to be able to work with the rest of the sections in that chapter. So we'll start with some definitions here. So what is a set? A set is any group or collection of objects. So for example, we can have maybe when you were young, you had a collection of dolls or a collection of marbles. Maybe you have a set of dishes at home. So it's any group or collection of objects. Those objects that are in that set are called elements. And so here a set can be designated in 3 ways. We can describe a set in words. So for example, I can say the set of dishes in my home, or we can use something called a roster form, where basically you list all the elements inside of these braces. The roster form is probably the form that is used the most for this class. And then the other way that we can write it is a set builder notation. And this set or this form is used a lot in other math classes. And so we'll be able to look at all 3 examples throughout this presentation. We'll revisit what all of this means here in this picture later in the slides. Okay, so for now, we're going to focus on the first 2 bullet points. At any time, if you have a question, please let me know. Don't be afraid to share your answers. Sometimes I ask, go ahead and try it, or does anybody have a possible solution? So you can feel free to put those in the chat as well. So here we have example 1, write a word description for the set. So they give us a set here. We use capital letters to name a set. And so this set is A, B, C, D all the way to Z. So what would be a way for us to describe this set? So what is it that we're seeing here? Any ideas? Anybody want to take a shot at it? What are these called? Any ideas? So these are all letters where in the alphabet. Okay. So let's see what our answer is here. Okay, so here we have our word description would be that set A. So we always want to identify the set. So set A is a set of letters of the English alphabet. And that would be it. Okay, so it's just a description of what this is in words. Now example 2, write a word description for the set March and May. Okay, so if we look at this example, March and May are what? These are months, right? But what is special about March and what is special about May? They both are months that start with the letter M. So my description here would be that the set B is a set of all months that start with the letter M. Okay. Now let's try some more examples here. Now, another way, if a student says that set B is the 3rd and 5th month, then that would also be correct. Okay, so you can describe the set in as long as it makes sense, then it would be correct. So when we get into the roster form, we have to be familiar with some of these basic number sets. So we have something called the natural numbers, or sometimes we call them the counting numbers. But these numbers are numbers that start at 1 and they go on forever. So remember last time we said that the 3 dots here represent the ellipses, so it means that these numbers are going to continue. And then we use the letter n to name the natural numbers. So we say that the set n is equal to 1, 2, 3, 4, 5, and it goes on forever. The whole numbers is very similar to the natural numbers, but the big difference here is that the whole numbers begin with 0. Okay, so instead of n starting at 1, it's going to start at 0. So again, if you're here for 2412, make sure you click the link to go to the other room. And I think they'll repost that just in case. So the next set of numbers that we have are the integers. And we use the letter I to represent the integers. And the integers are made up by the number 0, the natural numbers here, which we also call positive numbers. And then we also have the negative numbers. So these are called integers. And we'll be talking about these number sets throughout the presentation. Then we have the rational numbers. The letter that we use for rational numbers is Q. And this is just the set of all terminating or repeating decimals. Basically, we can write them as a fraction of 2 numbers, but they have to be terminating or repeating. So for example, half is a rational number. 0.5 would be a rational number. The number 4 is considered rational, okay, because we can write 4 as 4 divided by 1. We also have a third, and then we have this one here, 0.37. If you see a bar on top of a number, it means that the number is going to repeat. So here the bar is on top of the 3 and 7, so it repeats as 0.37, 37, and 37. So the rational numbers, there's way more than just the ones that I listed here. So the next set of numbers is the irrational numbers. And we can use J to represent those. And these are all numbers that are not terminating, so they don't end like the half, and they're non-repeating decimals. So a good example of an irrational number would be pi, because pi is 3.14, 15926, and you could barely see my 3 dots here, but they're here. Okay, so this number goes on forever, but it's not a non-terminating, and it's not repeating. So I apologize about my phone here. Let's just ignore it for a little bit. All right, so the next one. So now that we know these numbers here, we can use this to do the next example. So use a roster form to represent the following sets. Remember, whenever they ask for the roster form, you're going to be using these braces. Give me a quick second. I was trying to hang up the phone and I put it on speaker. So, all right. So remember, so your key terms here is roster, the roster form. So your answer should be in braces. So it says the set of days of the week. So what are the days of the week that we have? Today is a special day, right? Because it's Friday, happy math hour. So one day of the week is Friday. What are some other days that we have? Any suggestions? So we have Friday, we have Thursday, we have Monday, Tuesday, right? So if we want to write it in roster form, then we will write it as, don't forget your braces here, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday, and then we close our braces. If you want to, if they don't specify, you can go ahead and give it a name if you like. Okay, so, but here they don't tell us the set A, but if the problem tells you the set A is a set of all days of the week, then you want to go ahead and name it, okay? The next one, the set of the months that start with the letter A. So we have January, February, March, April. So April starts with A. And then we have May, June, July, and then we have August. So we would write it in braces, right? So then we have August and April. Does it matter if I was to write, and if I was to write April 1st, and then followed by August? Okay, so in the order in which we write the elements doesn't make a difference. Okay, so this is the same as this. They just happen to be written a different way, but they're still the same set. Okay. All right, let's continue. Use a roster form to represent the following sets. So we have the set of natural numbers less than 5. Okay, so we have, so just so that we remember, the natural numbers are 1, 2, 3, 4, 5, 6, 7, 8, and it goes on forever. So this problem wants us to write the set of natural numbers less than 5. So first, we need to make sure we know what the natural numbers are. Then we're going to choose all the natural numbers less than 5. So here's my 5. So anything less than that is going to be part of the set. So my answer is going to be 4, 3, 2, and 1. Okay, so we have 1, 2, 3, and 4. So these numbers here are less than 5. And so that's what makes up our set. Any questions? Okay, so the next one, the set of negative integers greater than -4. So you want to identify the keywords here, right? So one keyword is to know what number set you're working with. So we're working with integers. And so if it's helpful, you can write down the whole list here. That way we see it. Then another keyword here is negative and greater than. Okay. So I'm going to identify my -4, which is right here. And then I want to find all the numbers, negative numbers, that are greater than -4. So is -5 greater than -4? No. So the ones that are greater are to the right. So that would be -3, -2, and -1. Oh, but what about 0, 1, 2, 3, 4, and so on? Those are also greater than -4. But the keywords was negative. Okay. So we're only going to consider -3, -2, and -1. So my answer would be -3, -2, -1. But it's very important that you also include your braces. Okay. Because if you only write your answer as -3, -2, and -1, then that is not going to be considered a set. And so this would be incorrect. Okay. So you want to make sure you include those braces. All right. So now some more definitions. So a set is well defined if it is possible to determine whether any given item is an element of the set. Okay. So basically, if you can identify the elements of that set, then it's going to be well defined. So for example, is the set well defined? I guess that should have been my title above A. But the set is the set of letters of the English alphabet. Okay, so the set of letters of the English alphabet. So when you want to determine if the set is well defined, you want to ask yourself, can I list the elements of this set? Okay, so, and the answer to that is yes, right? We can list the elements of the English alphabet. They are A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, and Z. So those are all the letters in the English alphabet set. Therefore, I can say that the set is well defined. Okay, so as long as you can identify them, then you know that it's well defined. The set of great songs. So Mr. Carizales, what is a great song for you? Can you share that with us? One of your great songs? Kids. Okay. One of my favorite great songs, any Boys to Men song is a great song. So they are going to be in that set, right? So what is the problem here? Can I identify the great songs of this in this world? So the problem here is that what is great for me, okay, what is great for me might not be great for you, or it might not be great for Miss Patricia, or it might not be great for Miss Flores, right? So we all have a different opinion of what a great song is. So it's very hard to determine what those songs would be. And so therefore, it's not going to be possible to identify them. So we say that the set is not a well-defined set. Okay, because there's no standard to make such a judgment, because we all have different definition of what great means. Okay, so that is an example of well-defined. Now, some more definitions, right? So when I was in graduate school, my first class I took, there was a whole bunch of symbols that looked like, these were some examples, but there was a whole ton. And so one of my professors said that the reason math has a lot of symbols and we write in symbols is because mathematicians are lazy. And so, and you'll see why, right? So here, the symbol, if you see this E looking symbol, that little one symbol just means is an element of. So instead of writing all of this, we just use that symbol. Okay. Or yeah, it's probably the penmanship. Yeah. So here, if it has a line going through that same symbol, then we say is not an element of. Okay. So if you're taking this class, I would recommend to make a little table and start putting these symbols in there, right? So you can make your table, because a lot of this section, if you don't know the symbol, then that's going to make it difficult to answer any questions, right? So I would put the symbol, and then what does it mean? So you can put is an element of, and then maybe make a third a third column and write an example, okay? And then that can help you study for your homework or test or whatever it is. So here we have an example. Determine whether each statement is true or false, okay? So just true or false. 5.2 is an element of 1, 2, 3, 4, 5, 6. Okay, so that is how we read this. 5.2, and then you have your symbol, which means is an element of 1, 2, 3, 4, 5, 6. And so another way you can think of is an element of is basically it's asking you, is 5.2 or does 5.2 belong, is 5.2 inside of this set? And we don't see it in here, right? So this is not an element. So we're going to say that this is false. So this is false because 5.2 is not in this set here. Now let's look at letter B. -1 101 is an element of I. So first we need to figure out, well, what is I? Okay, so what is I? So remember earlier we said that I was the set of all the negative numbers, right? So all negative numbers. I'm just going to put NEG for negative, 0, and all the positive numbers. Okay, so those are your integers. So I stands for integers. Okay, so the big question to answer this question is negative 101 inside of this set? And so we can see that 101 is a negative number, and negative numbers are inside of my set I. So this one's going to be true as well. All right, so the next example is 2.5 is an element of W. So we need to know what W is. W is representing our whole numbers. And so whole numbers begin at 0, right? And then it goes to 1, 2, and so on. Okay, so the question you want to ask yourself is 2.5 inside of this set? Is not part of the set. So don't forget, if it has a line here, then that means it's not an element. So 2.5 is not part of that whole number set. True or false? Okay, so 2.5 is not in here, so then this makes it a true statement, right? So that's going to be true because 2.5 is not a whole number. The set of nice cars. True or false? So what is a nice car? For some of us, a nice car is just something that runs, right? It is working. And then for some of us, nice means a Lexus or a BMW. And so it's hard to make that identification. And so we say this is false. So actually, and so we say this is false. So actually, this one is probably, so this question here is more for, is it well-defined or not well-defined? And then that would make better sense. So this is not a well-defined set. All right, so there are some more definitions, right? So another definition is the empty set, or we call it the null set. And the way we represent it, or the symbols, if you have a circle with a line through it, that represents the empty set. Or if you have braces with nothing in it, then that's the empty set. Okay, so for example, the set of natural numbers that are negative integers. Okay, so the natural numbers, remember, they start with 1. So it's 1, 2, and so on. Okay, so if we wanted to write this in roster form, it says the set of natural numbers that are negative integers. Well, then there's no such thing. So my answer would just be an empty braces, or you can draw your circle with the line through it. And because there's no negative natural numbers, okay? So earlier, when we began this presentation, I gave you a picture of the set builder notation. And so let's go ahead and look at an example for that. So for the set builder notation, this is an example for the set of natural numbers greater than 7. But the way it looks is you're going to have your braces. So it almost looks like a roster form because it has the braces. Then you're going to have a variable, in this case x. You have a vertical line, and then you have some more information here, and then we close it with the braces. So the way we read this whole statement here is the braces tell you that that's a set. So we say the set. And then we have x, right? So for x, we say the set of all elements x The vertical bar here just means such that. And then the conditions, so these are the conditions of the set. So here, what does this mean? X is a natural number. X is an element of the natural numbers. So that's what this means here. So that is what we have here. X is an element of the set of natural numbers. And X has to be greater than 7. Okay, so this is how we would write that. So again, since you have braces, that tells you it's a set. We're looking at all elements of X. The vertical line here tells you such that. Then we know that X belongs to the natural numbers and that it's greater than 7. Okay, so that is how we would read the set builder notation. So let's do a couple of examples. Use the set builder notation to write the following sets. So it says the set of integers greater than -3. Okay, so what are the conditions? So when you're doing these, you can list those conditions. They have to be part of the integers. And what letter do we use for integers? We use the letter I, so we can use I. And then what else do we know? It has to be greater than -3. So, and it has to be greater than -3. Okay, so what we're gonna do is we're gonna write it as, here's my brackets or my braces for representing that it's a set. So we have our X, so for all elements of X, such that, here's my conditions, X is an element of the natural numbers, and X is greater than -3. Okay, and so that would be our set builder notation. So take about 30 seconds, see if you could come up with this one, right? And so I can get you started. We know it's going to be a set, so we'll have our braces. We're going to have our lines such that. And then in here, you're going to have your conditions. What are your conditions? It's a whole number, and it's less than 1,000. Okay. So my symbol for whole numbers, W. Okay. And so we're going to have X. So the set of all X such that X has to be what? An element. The symbol for element is the E here. It has to be an element of the whole numbers. And so we'll put and here. It has to be less than what? 1,000. So when I click, you'll see it a little bit cleaner here. So let me click. So we have our X such that X is an element of W, and X should be less than 1,000. So just change the symbol. X should be less than 1,000. Okay. So now we get into some more definitions. A set is finite if the number of elements in the set is a whole number. Okay, so if you can count them, then it's going to be a finite set. The cardinal number of a finite set is a number of elements in the set. So whenever you hear somebody say, what is the cardinal number of set A? All they're asking is, how many elements does the set have? Or they might ask, what is the cardinality of set A? So the answer is, how many elements are in that set? The symbol for cardinal number, or to get the cardinal number, is an N with the parentheses A. So if you see this symbol, it's just asking how many elements does it have? Okay, so how many? Or what's the cardinality? So for example, what is a cardinal number? So once you see cardinal number, that just means how many things are in this set. So if we count them, we have 1, 2, 3, 4. So we would say that the cardinality for this set is going to be 4. Okay, and we write our answer as this. Okay, and we use A here. That's the name of the set. So that would be the name of the set. So let's try some examples. Find the cardinality of each of the following sets. Okay, so we have J is equal to 2 and 5. So our cardinality for J, so we would write N because we're going to give our answer, and then our J. And how many things does J have? It has 1, 2. Okay. So here's just an explanation of that solution. And then letter B, we have 3, 4, 5, 6, 7, ... to 31. So before we get the cardinality, is this set finite? Do we actually know how many elements are in there? And the answer to that question is yes, right? What about this set? If you had something like this, ... is that set finite? Is that set gonna be finished? Can we say that there's so many elements there? And here we know that this is gonna go on forever, and so it's going to infinity. So it's not a finite set, it's an infinite set. Okay, so let's go back to the actual question, the cardinality of S. So the question there, you see the word cardinality, it's asking you how many things are in this set, or how many elements are in here. Okay, so one way you can do it is list them all down. So we would have 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, all the way to 31, and then you can count them, right? Or we can try to save some time and say, okay, what if I had 1 through 31? How many numbers would that be? So that would be 31 numbers, right? But we're not including the number 1 and 2, so now we can subtract them to get our answer. So 31 minus those 2 numbers would be 29. So again, you can list all the numbers if it's easier for you, or we can consider if it was from 1 through 31, then we know that's 31 numbers, but we're not including 1 or 2, so that's why we're subtracting 2 to end up with 29. Okay, now the last one. What is the cardinality of this number? Is it must be 4 because there's 1, 2, 3, 4, or is it 3? Okay, so if you notice in the set, you have 2 numbers that are repeated. Okay, and so when you have 2 numbers that are repeated, 2 numbers that are repeated. Okay, and so when you have 2 numbers that are repeated, we only count them once. So here, to find the cardinality, we're only considering this as 1 number. So then we have 2 numbers with the 7 and 3 numbers with a 51. So the cardinality of T is going to be 3. So if you see a number that's repeated, then we only count it once. All right, so now we have a few more numbers. A few more definitions. So we have equal sets. So set A is equal to set B, denoted by A equals B, if and only if they have the exact, exact same elements. So we look at this set and this set, we have a D here, and we have a D here. We have an E here, we have an E, we have F, and we have F. So they have exactly the same elements, okay? So we say that these are going to be equal because they're exactly the same. Okay, another definition is for equivalent. So a set is equivalent. Okay, so a set is equivalent if and only if A and B have the same number of elements, so the same cardinality. And the symbol that we use is this right here. So if you see this symbol, that just means, are they equivalent? Okay. And so in order for them to be equivalent, the cardinalities must be the same. They don't have to have the same elements as long as they have the same number of elements. So let's look at some examples. State whether each of the following pairs of sets are equal, equivalent, both, or neither. Okay, so here we have one set. So they want to know, is this set equivalent, equal, both, or neither to this set? Okay, so we can look at the first, are they equal? Well, no, right? Because they don't have the same elements. So they're not going to be equal. All right, so equivalent. In order to find out if they're equivalent, their cardinality has to be the same. So this first set has 1, 2, 3, 4, 5. So this one has 5 elements. So this one has 5 elements. And this one, the second one has 1, 2, 3, 4, 5 elements. So they have the same number of elements, or the same cardinality. So we're going to say that these are equivalent. Okay. So they're not equal, but they are equivalent since they both have 5. So for letter B, we have 4, -2, 7, and the second set is 3, 4, 7, 9. Well, they're not equal because -2 is not in this set, and 3 and 9 are not in the first set. So they're not equal. Equivalent. Well, the first set has 1, 2, 3, and the second set has 1, 2, 3, 4. So they're not equivalent, right? Because one has 3 items, one has 4 elements. So not equivalent. So we say neither. Let me give you one more. I'm going to write it here. So what if we have 1, 2, 3, and we have 3, 2, and 1. So are these two equal? So is this equal to this? The answer is yes, because they have the same elements. Okay. So I guess I can stop, right? But no, we also have to check, are they equivalent? So this has 3 items, and this has 3 items. So they have the same cardinality. So they are going to be equivalent. So my answer here would be that they're both. They're both equal and equivalent. Okay. And that was just the explanation for that. So now we're going to move on to some other terms. We have something called, when we're looking at sets, we consider something called the universal set. And we use the letter U to determine that universal set. And so, for example, we're going to talk about Venn diagrams in a little bit. But you could think of the universal set like if we have a box, everything in this box is going to be your universal set. So we call it, we put a U here. If you have, let's say, a subset, which we'll talk about that in a little bit, and let's say you have the numbers 1 and 2, but if the universal set is 1 through 5, let's just make it small here. Okay. Then what that means is that in working with this problem, the only numbers that we would consider are 1 through 5. Okay. That makes up your universal set. And since A doesn't have 3, 4, and 5, they're going to be out here in the box. So The only numbers we're considering are 1, 2, 3, 4, and 5. And so the universal set is everything in this box. Now the complement of a set is going to be all the elements that are not in that set. So if I was to ask for the complement of set A, then we use this symbol, okay? So if you see this symbol, that means the complement of set A. And all that means is, what are the elements that are not in set A? So what is everything that is not in this circle A? Well, those numbers are 3. So we would write our 3. 4. So well, those numbers are 3. So we would write our 3. 4. So we would write our 4. And 5. We would write our 5. So that would be our complement. What about the number 6? Well, 6 is not an A, but it's not part of our universal set either, so we're not going to consider it. And so this would be our answer. Okay, let's see if I have an example, some examples here. So here we have U, which is our universal set, is 1 through 10. S is 2, 4, 6, and 7. And then we have another set T, which is, we'll talk about T in a little bit. But it says find S complement. Okay, so S complement. So if we want to find S complement, then what you want to ask yourself is, what are all the numbers that are in the universal set that are not in the set S? So if we look at the set S, well, let's look at the set U. So is 1 inside of S? The answer is no. So then that belongs to our complement, so we would have our 1. Is 2 inside of S? Yes. So we move on. Is 3 inside of S? No. So that's part of our complement. So it's all the numbers that are not in S. 4 is in S. 5 is not in S. 6 is in S. 7 is in S. And 8 is not. 9 is not. And 10 is not. So again, the complement is just everything that's not in that set that is part of the universal set. Oh, so maybe I should have, let's go back here so you don't see the answer for the next one. All right, so any questions on that one? So for the next one, we have, they give us T. T is an element of all the odd counting numbers. So we're looking at 1, 2, 3, and so on, that are less than 10. So what are those numbers? So let's write down what T is first. So it makes it easier to write it in roster form. So X is an element of the odd counting numbers. So the odd counting numbers are 1, 3, 5, 7, 9, 11, 13, and so on. Okay. But the ones that we're interested in are the ones that are less than 10, right? So 1, 3, 5, 7, and 9. So this is our T. So to find the complement of T, it's going to be all the numbers that are in the universal set that are not in here. So we have 1, 1 is here, 2 is not there, 3 is there, 4 is not there, 5 is there, 6 is not, 7 is here, 8 is not here, 9 is in here, and 10. Okay, so when you're doing these problems, if they give you something in set builder notation, if you write it in roster form, it might be easier to see what those numbers are. Then you find the complement. Okay, so again, complement just means everything that is not in the set that is part of the universal set. Okay, so let's go on. subsets. So subsets. A set A is a subset of set B. And here's another symbol that you can add to your list of symbols. Okay. If and only if every element of A is also an element of B. Okay, so if you see this, they're going to ask you most likely true or false questions, right? What it means is that every element that you see in here has to be in here. Okay. If they're not, then it's not a subset. So for example, before we do some other examples, let me just give you a short example here. Let's say you have 1 and 2 for A, and B is 1, 2, and 3. And if I asked you, is A subset of B, then all I'm asking is, are all the elements of A inside of B? Okay, so are all the elements inside of A, are they also in B? So we have 1 and 2, and we have 1 and 2. So they are, everything here is in here. So we say this is true. Okay. But what if I asked you instead, is B a subset of A? Okay, so now we're asking, is everything in B right here, is everything here inside of A? And the answer is no, right? Because A is missing 3. So this is going to be 8. And the answer is no, right? Because A is missing 3. So this is going to be false. Okay, and we'll get to practice here with some more here. If you have a bar through your subset symbol, that just means that it's not a subset. It's not a subset. And the empty set is always part of every set. So the empty set is always inside of every set. Okay. The first one here, A is a subset of A. Is always true, and the reason is, let's say A is 1 and 2, and B is 1 and 2. So this is A, and let's say, well, this is A also. And if we want to know if it's a subset, then we're asking ourselves, is everything here inside of here? And the answer is yes, and so that's always going to be true there. Right, so let's try this first one. So we have 5, 10, 15, 20 is a subset of 0, 5, 10, 15, 20, 25, 30. So again, you have your symbol subset. What that means is everything here inside of this set? Okay, so let's check. So we have 5 in here, and 5 is in here, so that we're good on that part. 10 is here, 10 is here, 15 is here, 15 is here, 20 is here, and 20 is here. So everything here is inside of this bigger set, so we say this is true. I'm just going to put TR. All right, let's go to letter C first, and then we'll come back to B. So here is everything is 246 a subset of 246. So is everything here inside of this set? And the answer is yes. So this is also going to be true. And then the last one is the empty set apart. Is the empty set inside of this set? And the answer is yes. So this is going to be true. So remember that the empty set is going to be inside of all sets. So then this is going to be true. Now here, they have W as a subset of N. So as you're doing these, if you're not sure what W is, you can write out the numbers. So remember, W is 0, 1, 2, and so on. And then N is 1, 2, 3, and so on. So they want to know, is W a subset of N? And again, if it helps you to write it down, you can. So this is 0, 1, 2, and it goes on forever. Is that a subset of 1, 2, 3, and so on? Okay, so we ask our question, is everything in here inside of here? Well, let's check. So 0 is missing from this second set, okay? So then this is gonna make it false. But what if we had reversed it? If you reverse it, then it does become true, because all of the natural numbers are part of the whole numbers, okay? All right, so these were just my answers there. The Venn diagram, I kind of drew a picture of it right now, but the Venn diagram is a way for us to identify subsets. So that you have the universal. A is considered a subset of U because everything in A is inside of U, as we can see in the picture. And let me see, everything outside of A. So if you have any numbers, so everything outside, so like if you have something in here outside of the circle A, then that's your complement, right? Because they don't belong to A. One more definition, a proper subset. Remember, so this right here looks a lot like that one, okay? The only thing that is missing is the line on the bottom, which represents equal. So in order to be a proper subset, the sets cannot be equal. So for example, if I have A is 1 and 2, and B is, and B is 1, 2, and 3, and you want to see if A is a proper subset of B, then it still has to be a subset in order for it to be a proper subset, right? So first you want to ask yourself, is everything in A inside of B? So A has 1 and 2 and B has 1 and 2. So it meets that criterion. So everything in A is inside of B. Now the second criteria is that they cannot be equal. In other words, the second set better have an extra thing hanging out, okay? So here we have a 3, so it has an extra item. That means that A and B are not the same. So here we say that A is a proper subset of B. If you had, let me just write one more here. Let's say C is 1 and 2. If I ask you if A is a proper subset of C, I guess I could have used a different, let's use E. Is A a proper subset of E? Well, here they do have the same elements, or the elements of A are inside of B, so that meets that criteria. But the problem here is that A and E are the same, and that cannot happen. So this would be false, okay? So let's try an example. I think I have one here. Well, I forgot to take the answers out, but let's check. So the question here is determine if the first set is a proper subset of the second set. So the symbol is this one here. So 1 is A in here, yes. Is E in here? Yes. Is I in here? Yes. Is O in here? Yes. Is U here? Yes. So that makes it a subset. Does the second set have an extra element? And the answer is no, there's no extra element. So this is going to be false. Okay. So let's see. Let's go to this one here. So the question is whether N is a proper subset of I. So remember N, let me write it down here. N starts with 1, 2, 3, and so on. And we want to know, is that a proper subset of I? I has -2, -1, 0, 1, 2, and so on, right? Okay, so let's ask ourselves the question, is 1 in here? Yes. Is 2 in this set? Yes. Is 3 in this set? Yes. So that's a good thing. Now the last question you want to ask yourself, does this set have at least one element that's not over here? And the answer is yes, it has these extra things. So this is going to be true. It is a subset. Okay. Let me see. Let me skip this. This is just asking about subsets. Intersection, I have 3 minutes. I think I can at least cover intersection, maybe union as well. But intersection is basically you're given 2 sets. So I'll let you read all this. But basically you're given 2 sets. And well, before I do that, this is a symbol for intersection. And your answer, if they ask you what is the intersection of A and B, basically it's going to be all the elements that are common to both of them. So for example, if you had a picture here for the Venn diagram, the elements that are common to both A and B, that's going to be your intersection. Okay, so if I had some numbers here, let's just make up some numbers. 1, 2, 3, and 4 out here. Okay, the elements of A are 1 and 2 because they are in the circle A. The elements of B are 2 and 3. Okay, and the elements of U, the universal set is 1, 2, 3, and 4. Okay, so if you want 3 and 4. Okay, so if you want to find the intersection, we're writing it as A intersected with B. That's going to be a set. You want to ask yourself, what are all the elements that are common to both set A and B? So in the picture, we can see that 2 belongs to A, but it's also belonging to B. If you don't have a picture, then we can look at the sets here, and they both have 2 in common. So my answer would be 2. Okay, let's do one last one. If we have A is 1, 4, 5, 7, and B is 2, 3, 4, 5, 6, what is A intersected with B? They want to know what are the common elements. So A has 4, and B has 4. A has 5, and B has 5. And that's all that they have in common. For A and C, what are they having? For A and C, 3, 6, 9, A is 1, 4, 5, 7. They have nothing in common, so we use the empty set. So when you have no common elements, we use the empty set. So if you want to download, because there's some more slides here, if you want to download the presentation, on the right side of your screen, you should see a little box with an arrow pointing down, so it looks something like this. If you click on it, it's going to let you download the presentation. Next week, I will finish doing Venn diagrams and then a little bit more stuff there. But thank you for joining us today, and I hope that you have a great weekend, and we'll see you all next Friday.
Thank you, Ms. Truca, for your wonderful presentation. So again, we do want to remind you guys that you could download that presentation while it was up on the screen. And we do definitely want to remind you guys about the previously recorded sessions, which are available on a YouTube playlist. This session will also be available on that playlist later today. And before you all leave, I want to share the TVE session that we will have next. At 1 p.m. today, we will have a presentation from the Open Computer Lab and ISC, and we will be back next week at 11 a.m., where Math 1332 will cover application of sets and the exam 1 review, and Math 2412 will cover the inverse trigonometric functions. Our 1 p.m. session next week will be a presentation on Hack the Border, overview, and purpose. Thank you all for coming in today. We hope you all have a lovely weekend, and if you have any questions, feel free to use the chat box or your mic. We hope to see everyone again for Happy Math Hour.